Alright, welcome back. Let's continue our discussion in these flexural members, and right now we are going to do a couple of sample problems. Now for our first sample problems regarding this bending stress and bending strain, this one is taken from the textbook by Python and Kisalas, and this is sample problem 5.2. The problem states that the simple supported beam in the figure has the T-shaped cross-section as shown. Determine the values and locations of the maximum tensile and compressive bending stress. So here's our cross-section of this beam. So if you cut a section right here, and that's going to be the shape. And we have here 6 inches, 0.8 inches thick. And for the leg right here, we have 8 inches. And the beam is loaded in this manner. We have a distributed loadings and a point load right here, or concentrated load of 1,000 pounds. 1,000 pounds, and the distributed load is 400 pounds per foot. And the distance from A to B, this is 10 feet, and B to D, this is 4 feet. Okay, so actually the book has given the shear and moment diagram to probably to save time, and of course we have done videos for that, sample problems for that. So here's the loading diagram, so the support reactions, and once you have all these, then you can draw, you can construct the shear and moment diagram. And by the way, the distance here, this is 4 feet. And from the shear diagram, we can obtain this moment diagram. And the maximum point is where the maximum moment would be, where the shear crosses, or I mean where the shear is zero, or where the shear crosses from, let's say from positive to negative, or negative to positive. Okay, so that's one point. I mean, that's the local maxima or minima, right, from the subject of calculus. And here's another one. It's where the shear crosses, and right here we have, I mean, right here we still have another point where the velocity sorry, where the shear crosses from positive to negative, and our value is negative 4,000. And the difference actually is that if you have a positive moment, then the bending would look something like this, right? And if you have a negative moment, then that means that the bending would be something like this. Okay, so in terms of location of tension zone and compression zone. So for positive moments, our tension zone is right here at the bottom. And right here, if you have a negative bending moment, then the tension zone would be right here. Okay, so we are going to evaluate this beam, this cross section, using these two values later on. Okay, so first step, since we have the the maximum moment right here, we have 3,200 pound foot, and we have a negative 4,000 pound foot. So we have the internal force. Then um, what we need is, let's write it here, before we can apply the flexure formula. Determine first the centroid. Okay, so we have to locate where the centroid of the section is, because it's not given, and this is not symmetrical, so it's not going to be halfway. Okay, so um, to do that, let's draw it here. So let's divide this T section into two areas. So we have these two areas, and since these are basic shapes, And what that means is that, for example, here's our centroid for this area. Let's say this is area 1, right? So this is area 1 and this is area 2. Okay, and the centroid for area 2 would be halfway of this length, and this one would be halfway of this length. Okay, so let's label this. Now let's say this is y sub 1 bar. That's the distance to the centroid, and let's say here's gonna be our reference line, and from this reference line to this one, to the centroid of the area 2, that's gonna be y bar sub 2. Okay, and somewhere there's gonna be the final centroid of the combined shapes would be maybe something, maybe somewhere here. Okay, and that's gonna be our neutral axis. Okay, now the distance from this to the neutral axis, let's just call it y bar. Okay, so now let's solve for the y bar. We are going to solve for the y bar, and to solve that, it's just actually in the statics, static class. So it's just simply summation of, since we have composite shapes, then that's just going to be AI. So that means that we have A1 and A2, summation of A1 and A2, actually the product, okay, divided by the summation of the AI alone. Okay, and that simply means that we have A1 y bar 1 plus A2 y bar sub 2 all over summation of area, which is A1 plus A2. And this will be, okay, if you substitute all the values, we have the area is, from these dimensions, we have 8 times 0.8, that's going to be 6.4 times the distance. So from the reference point, or from the reference line to the centroid of this first shape, since this is 8, the total length is 8, then this is just going to be halfway, then that's just going to be 4 inches, right? So this one is inch to the fourth, inch squared, and this one is inch, okay, plus the area of the second shape, that's 6 times 0.8, this is 4.8 inch squared, times the distance from the reference line to the centroid. So if this is 8 and this is 0.8, so that means it's gonna be 8.8.04, right? So we have here 8, and half of 0.8 is 0.4, so that's gonna be 8.4 inches. Now divided by the area, 6.4 inches squared plus 4.8 inches squared. Now the distance would be 5.886 inch. Okay, so from this reference line to the centroid, to this total centroid or overall centroid, the value is 5.886. Okay, so let us redraw this. Here's our centroid. Here's going to be our neutral axis, and the distance, this is 5.886, right? 5.886, and if this is 5.886, then our total is 8.8 minus 5.886. It's gonna be 2.914. So this is 2.914, right? So that's gonna be our distances from the neutral axis. Okay, now that we have the centroid, then I think we still need the value of solving now for the moment of inertia. And since this is a composite shape, then that means that the I total is just simply I sub 1 plus I sub 2. So the moment of inertia of this shape plus the moment of inertia at this shape, but the axis of rotation is taken at this neutral axis, at this 5.886. Okay, so let's solve for I sub 1, and this is our I sub area 1, right? And this is our area 2. And we need the distance from the neutral axis to the centroid. So we have here the centroid, right? The centroid of this shape, and we have here the centroid of this shape. And what we need are the distances, or these distances. Okay, so how do we solve that? Then it's just simply subtraction or addition. We have 5.886, and we know that this is if this is 8, then this is just 4, right? And the distance from this to the centroid of the second area, that's just 8 point, we know that this is 8.4. Okay, so therefore this value, this distance right here, is just simply 5 this is just 5.886 minus 4. So we have 1.886. So let's write it here. 1.886, and this is negative. Why? Because from this reference point, or from this reference line, then this one goes downward, so that must be negative. And right here is that's 8.4 minus 5.886, and we have 2.514. 2.514. Okay, so again, based from this reference, if this is our reference line, then this will be negative because it's downward, and this one is positive because it's upward. Now, in terms of equations, uh, if you prefer equations rather than doing the geometry, then the actual equation is actually this one. We have a summation of the moment of inertia, okay, I, so something like what we did earlier. Is just or it's just a statistic, a symbol. So plus the area I times this one, the distance to the centroid, okay, minus y bar squared. Okay, so here's going to be the working equation. And the basic equation actually for the parallel axis theorem is just I plus let's say I sub x or I sub y plus the area times the distance squared, right? So here's the parallel axis theorem. We are going to use this because the axis of rotation is not passing through the centroid. So here's the actual axis of rotation, and the centroid is right here. So that's why we are going to use the parallel axis theorem. So here's the basic equation, and for a composite shapes, then you can just use this one. Or in terms of graph, if you are convenient with it, then I think that's fine. Okay, so let's solve now. Let's continue. So for our I sub 1, we have here the I sub x. Since it's a rectangular shape, then it's just 1 over 12 base times h cube plus, right, the area times the distance, right? Distance squared. Okay, so let's substitute the value. 1 over 12 times base. What is base? What is this? This is 0.8 times the height. And the height here is 8. So 8 cube plus the area. The area is 6.4 times the distance. The distance, you can use this equation if you want, or we can use this one. So we have negative 1.886 squared. And if you do the math, our value right here is 56 point. Let me just write 56 point. I think 56.9 inch to the fourth, or 898. Okay, 56.898 inches to the fourth. Okay, so that's our I sub 1, and for our I sub 2, it's just the same. We have, since this is a rectangular shape, then it's just going to be 1 over 12 base times height. But the height right here is this one, the 0.8. Okay, plus the area times the distance squared. Okay, so 1 over 12 times the base, this base, that's 6 times 0.8 cube. Okay, plus the area of 4.8, that's the cross-sectional area, and the distance of 2.514 squared. And this one is 30.59 inch to the fourth. And therefore, the total moment of inertia is I sub 1 plus I sub 2. This is 87.488 inch to the fourth. Okay, so here's our total moment of inertia. Now that we have the geometric properties, required geometric properties, such as this and this one's right here, plus the internal moments, then we can solve for the flexural stress. Okay, so I think this is number 3. Solving now for the flexural stress. Okay, so for flexural stress, I think we have to redraw the shape and draw the stress distribution. And here's our centroid right here. And for the stress distribution, this will be something like this. So actually, that depends upon which section. At which section or point. Like for example, here, if we use this value, then this is a positive moment, or if we use this value, then that's going to be a negative moment. But we are going to evaluate. We can just select the 4,000, simply because there's difference in the distance, right? So in the distance from the centroid to the bottommost surface, or to the topmost surface. So that's why at let's say at this point, we have a compression on top and tension at the bottom, but using this value, we have tension on top and compression at the bottom. Okay, so just for illustration, let's just use this. Or I think it would be better if we use tension on top. Okay, and let's label this, I think ABD. Let's label this point E, and this one point F. Okay, at point F, so we have this stress distribution. So we have tension here on top, and we have compression at the bottom. And the distance, recall that the distance, we have this 5.884, and this one is 2.914. Okay, so now let's apply the Flexural formula. So sigma b is just simply mc all over I, right? And the moment, because we are considering point F for now, let's consider moment is equal to negative 4,000. And the unit right here is pound foot. Okay, so we have sigma b, let's say the top, and we can have sigma b at the bottom. We'll have values for this. So if we substitute the values, we have negative 4,000, and the distance is 2.914 all over the moment of inertia of 87.488. So if you check the units, it should be consistent. This is in inch, this is in inch, and this one is pound foot. So therefore we have to multiply this by 12 to convert the foot to inches. Okay, so here's gonna be our value, and this will be 1599 psi. So that's the unit, because we convert this pound foot to pound inch. Okay, so pound per square inch. And for the bottom, it's just the same equation, and but the values right here, this should be 5.884, right? So again, times 12 divided by the total moment of inertia, and this one is equal to 2580 psi. Okay, and since this one is in compression, then this will be there must be a negative sign right here. So negative times negative, that's gonna be positive, and this one will be negative. Sorry, this must be okay. This must be 3,230 psi, and I think for the signs, this should be. I think we have to include a negative sign right here, because that's I think that's how they derive the equations. Because this one is in tension, so this must be positive. So there must be negative right here. Negative times negative, that's gonna be positive. And or I think that let me redo this one. Okay, let me redo this. This is sigma b. This is our working equation, mc all over I, right? And our value for moment is equal to negative 4,000 pound foot. Okay, and for if we solve the bending stress, or the maximum bending stress on top, then this is gonna be this should be, because the equation was derived using the top as negative, so this must be negative times negative 4,000 times 2.914 times since we need to convert this to inch, so this must be times 12 divided by the moment of inertia of 87.488, right? And this will be equal to 1599 psi. Okay, and for the sigma max at the bottom, then since at the bottom there should be no negative signs, so it will be negative 4,000 times 12, right, times the distance, except that we are going to use this distance 5.88, right? 5.886 or 884 times 12 times the 87.14 48, and this one would be negative 3,230 psi. Okay, so here the value right here This is compression because the bottom is in the bottom portion is in compression. This is 3,230 psi, and here is 1,599 psi. However, this magnitude right here for the stress, for the bending stress, only is only true for point F. Okay, at this point, now we are going to check the value of the stress at point E. Okay, that's right here. Evaluating now the stresses at point E. Okay, so for point E, then let's draw again the shape, and here's our centroid. And for the stress, this one, the top portion is in compression, and the bottom portion is in tension. And the distance is still the same. We have 2.914, and we have 5.884 or 886. Okay, so that's it. And the moment, we need to write the moment. The moment is positive, so let's write here m is equal to 3,200. This is in pound-foot. Okay, so our working equation again is sigma b is mc all over I, and the moment is equal to 3,200 pound-foot. Now for sigma b max on top, okay, so right here, so we said that the negative sign appears for the top portion. This is negative mc over I. So what's our m? It's positive 3,200, and we need to multiply this to 12. And the c, the distance from the neutral axis to the outermost fiber, that's 2.914 divided by the moment of inertia of 87.488. Okay, and the value right here is negative 1,279 psi. Okay, and for the sigma max at the bottom, this is equal to mc over I. What's our m? 3,200 times 12, and times the distance, 5.884. So 5.884 divided by 87.488, and our value right here is positive 2,580 psi. Okay, so therefore let's compare this. Let's compare the results. We have the value right here. We have for, or let's write, I think we should write if it's in compression or the signs. Right, let's write tension, and right here, here's the tension. Okay, so therefore the maximum stress, stresses are for tension, so sigma t max, that's gonna be 2,580 psi. Okay, at point, okay, at which point? This is at point E. So at point E, and for the compressive stresses, the maximum is, so we have 3,230 and we have 1,200. So the maximum is negative. I think let's just write the magnitude, 3,230 psi at point F. Okay, so here's our answer. Okay, so I guess that's a lengthy problem. I mean, sample problem. We still need to do some more, another type of sample problems regarding these flexural stresses and strains. So I think I have to do another video for the said sample problems.